Hello friends, today I will take you to another exciting journey into the world of spatial visualization. Spatial visualization is a cognitive ability that involves mental manipulation and transformation of visual information, particularly in a three-dimensional space. This skill plays a significant role in various fields, especially mathematics. Strong spatial visualization skills help to understand complex geometric shapes, visualize figures, patterns, and graphs from a 3D perspective. My purpose is to design a spatial visualization demonstration video especially for your age group, which will be useful to you in your mathematical performance. I have developed all figures and shapes in this program using Python 3.1 in IDLE shell. We will cover these aspects in today's session. Systems of three linear equations in three variables and planes. The standard form of this would be ax plus by plus cz equals d. We will also visualize right triangles in 3D. We will see a few geometric shapes and figures in 3D, and we'll see a few 3D surface plots of polynomial equations. We have seen in our math class that the graph of a linear equation with two variables creates a line which extends infinitely on both directions. A graph of a linear equation in three variables creates a plane which extends infinitely in all directions. Here, we will talk about systems of three linear equations in three variables and see how they can be visualized in 3D Cartesian space. The standard form of this is ax plus by plus cz equals d, with at least one of the coefficients being a non-zero. Now let's view some of the planes in a 3D space. Let's first look at the xy plane. The figure represents the xy plane, which is a two-dimensional plane that lies perpendicular to the z-axis. It divides the 3D space into upper and lower halves. The plane equation is the equation of the form z equals 0. This means that all points on the xy plane have a z coordinate of 0. The axis orientation is a figure that includes three axes, x, y, and z. The xy axes lie within the xy plane and are perpendicular to each other. Grid representation is the grid of the points on the xy plane that indicates and extends infinitely in x and y directions. Each point on the grid has coordinates x, y, and 0, where z is always 0. Now let's talk about the yz plane. This figure represents the yz plane, which is a two-dimensional plane that lies perpendicular to the x-axis. Plane equation. Without referring to any equation, we can infer that the equation of the yz plane is the form of x equals 0. This means that all points on the yz plane have an x-coordinate of 0 or remains constant. Axis orientation. Similar to the xy plane, the yz plane includes three axes, y, z, and x. The y and z axes lie within the yz plane and are perpendicular to each other. The x-axis is perpendicular to the yz plane. Grid representation. The grid of the points on the yz plane indicates that it extends infinitely in the y and z directions. Each point on the grid has coordinates of 0, y, z, where x is always 0. Now let's talk about the xz plane. This figure represents the xz plane, which is a two-dimensional plane that lies perpendicular to the y-axis. It divides the 3D space into a front and back halves. Without referring to the code, we can infer that the equation of the xy plane is in the form of y equals 0. This means that all points on the xy plane have a y-coordinate that remains 0. Similar to the previous planes, the xy plane includes three axes, x, z, and y. The x and z axes lie within the xy plane and are perpendicular to each other. The y-axis is perpendicular to the xy plane. The grids on the point of the xy plane indicates that it extends infinitely in the x and z directions. Each point on the grid has coordinates of x, 0, and z, where y is always 0. Now, let's review all the planes together. Each plane is marked in different colors and labeled accordingly for easy identification. As we can see, all are passing through the origin. The figures are represented in a perspective view, allowing viewers to observe the spatial relationships between the planes and axes from different angles and provide a visual representation of how three planes xy, yz, and xz intersect 3D space within the xyz coordinate system. Now let's come back to the system of linear equations in standard form, which is ax plus by plus cz equals d. If we set a equal to b equal to 0 and c equal to 1 and d equal to 4, the linear equation will be like z equal to 4. So how does the graph of this equation look like in a 3D space? It consists of every point in 3D space whose z-coordinate is 4 and xy is any real number. So the graph of this equation is a horizontal plane 4 units above the origin where z is constant at 4, meaning the plane is parallel to the xy plane and passes through the point 0, 0, 4. Likewise, equations y equal to 4 will represent a vertical plane, 4 units right of the origin on the positive y-axis, where y is constant at 4, meaning that the plane is parallel to the xz plane and passes through the point 0, 4, 0. X equal to 4 will also represent a vertical plane, 4 units right of the origin on the positive x-axis. X is constant at 4, meaning that the plane is parallel to the yz plane and passes through the point 4, 0, 0. Now, let's see how it will look like if we set coefficient of only one variable to 0. In this case, c is equal to 0 and a is equal to b, which is equal to 1. And the constant still remains at 4, which is d equal to 4. So the linear equation becomes x plus y equal to 4. Every point on this line is a solution to the equation regardless of the value of z. There can be infinite number of lines like this, and all these lines together create a plane. So, a system of 3 linear equations in 3 variables can be represented as a group of planes. Each plane can be oriented at any angle and positioned anywhere in space relative to other planes. Each plane graphically represents the set of solutions to one of the 3 equations. So any point which simultaneously falls on all 3 planes corresponds to a solution that satisfies all 3 equations and hence the system. These points therefore correspond to the solutions of the system. Next, let's look at how the 3 planes can intersect in a 3D space. First, if the 3D planes intersect exactly at only one point, and the system will have one unique solution. Let's visualize one such system of equations. Here we see the three planes represented by different colors and having the systems of equations like this. X plus y minus z equal to 1, negative 2x minus y plus 3z equals 4, and 5x minus 3y minus 2z equal to 1. These three planes intersect exactly at one point with the Cartesian coordinate of 3, 2, and 4. Thus, x equals 3, y equals 2, z equals 4 is a solution to the systems of equations with three variables. You can also plug in and verify. Now, let's consider another possibility of the three planes intersecting with each other. Two of the planes intersect to form a line, and if the third plane also intersects with the other two along the same line, the common points of the intersection for all three planes are represented by that line. The system will therefore have an infinite amount of solutions corresponding to every point on the line. Infinite number of solutions will also exist of two of the planes where all three planes are identical. Let's visualize the graphs for these three equations. 6x minus 3y minus z equals 3. 3x minus 9y plus 2z equals negative 6. 2x plus y minus z equals 3. If we actually solve the systems of equations in algebraic elimination method, we will get 0 equals 0. This indicates that the system has infinite number of solutions in both 2D and 3D. Now the third possibility is no solution. Anytime a system has two distinct parallel planes, there is no solution. Let's look at the plane. The two equations of the plane are 2x plus 3y minus z equals negative 20 and 2x plus 3y minus z equals positive 20. Here you can see two parallel planes that intersect the z-axis at two different points marked in the red dots, but they do not intersect with each other. Hence, there is no solution. The third plane can be distinct and parallel to the other two or intersect the other two. Regardless of its orientation, there won't be any points that lies common to all three planes. Here, the equation of the intersecting plane is x plus y minus 2z equals 0. Hence, the systems of equations in such cases will have no solutions. So we have seen various ways on how the three planes in a system of three linear equations in three variables can be oriented. These orientations can create a system with one solution, infinite number of solutions, and no solution. With this, we came to an end of our demonstration of systems of equations with three variables and corresponding planes in x, y, z coordinate systems. In this section, we will visualize a right triangle in 3D. This figure helps to visualize a right triangle in a 3D space. There are three sets of right triangles adjacent to each other. Let's consider the right triangle DAC, which has angle A at right angle. The side DC is the hypotenuse, also labeled as H. With respect to the angle ACD, marked as alpha in red, AC is the adjacent base and AD is the opposite base. If we apply trigonometric ratios on the angle alpha, we will end up having three trigonometry functions like this: sine alpha, cosine alpha, and tangent alpha. So sine alpha equals opposite over hypotenuse. The cosine alpha equals adjacent over hypotenuse, and tangent alpha equals opposite over adjacent. By understanding and applying concepts related to right triangles in three-dimensional space, we can solve complex mathematical performance, also make some important informed decisions in practical scenarios. Here are some of those. Visualization of 3D triangles. Understanding right triangles in 3D space allows us to visualize geometric relationships in 3 dimensions. This visualization can aid in understanding spatial concepts and solving problems involving three-dimensional objects and structures. Application of the Pythagorean theorem. The Pythagorean theorem, which states that the square of the length of the hypotenuse of a right triangle is equal to the sum of the squares of the lengths of the other two bases. So 8 squared equals base 1 squared plus base 2 squared. This extends to 3 dimensions. By applying the Pythagorean theorem in 3D space, we can find lengths of sides and distances within 3-dimensional shapes. Calculation of distances and lengths. In practical applications such as engineering, architecture, and physics, understanding right triangles in 3D space is essential for calculating distances, lengths, and dimensions of objects. For example, architects use trigonometric principles to design structures, and engineers use them to analyze forces and stresses in three-dimensional structures. Trigonometric solutions in 3D problems. Trigonometric functions such as sine, cosine, and tangent are fundamental in solving problems involving angles and sides of right triangles. In 3 dimensions, these trigonometric functions can be used to determine angles, distances, and orientations of objects relative to each other. Real-world examples. Practical examples where understanding 3D right triangles and trigonometric concepts are useful to include determining the height of a tall building or structure using angled measurements and distances. Calculating the distance between 2 points in 3-dimensional space, such as the distance between 2 cities on a map with elevation differences. Analyzing the forces acting on objects in 3 dimensions, such as the tension in cables supporting a bridge or the pressure exerted on a structure by wind or water. In this section, I have converted some advanced geometric shapes and figures into 3D to see how do they represent when visualized from a 3D perspective. Now let's look at them. This is a hexagonal prism. A hexagonal prism has 3 pairs of parallel faces, with each pair consisting of a regular hexagon, the bases, and the 6 rectangles, which are the lateral faces. These connect corresponding sides of the bases. A hexagonal prism has 18 edges in total and 12 vertices, which are marked in red and blue. The base of a hexagonal prism are regular hexagons, meaning all 6 sides are equal in length, and all interior angles are congruent, which measure 120 degrees each. The volume of a hexagonal prism can be calculated using the formula V equals area of the base times height, where the area of the base is the area of one of the base hexagons and calculated as a squared times 3 square root of 3 all over 2, where a is the side length of the hexagon. The total surface area of a hexagonal prism includes the area of the 2 hexagonal bases and the areas of the 6 rectangular lateral faces. This can be calculated by adding the areas of all these surfaces together. A hexagonal prism exhibits symmetry along its central axis, meaning that if you were to cut it in half along the axis, the resulting halves would be mirror images of each other. Understanding these geometric properties helps in visualizing and working with hexagonal prisms in various mathematical and practical contexts such as engineering, architecture, and geometry. Now let's visualize another shape. This shape is called a pentagonal pyramid. A pentagonal pyramid has 6 faces, 1 pentagonal base, and 5 triangular lateral faces. It has 10 edges. 5 of the edges are formed by the side of the pentagonal base, and 5 edges are the lateral edges connecting the apex to each vertex of the base. There are 6 vertices in total, including the apex and the 5 vertices of the base. We can see all of these properties in the figure along with its height. The area of a pentagonal base can be calculated using the formula for the area of a regular pentagon. The lateral surface area can be calculated by adding the areas of 5 triangular faces. The total surface area is calculated by the base area plus the lateral surface area. The volume of a pentagonal pyramid can be calculated using the formula V equals 1/3 base area times height. Now, let's move on to another section of visualizing 3D surface plots using polynomial functions. Creating 3D surface plots using polynomial functions is a common way to visualize various mathematical surfaces. Let's review a few examples of polynomial functions we can use to generate 3D surface plots. Elliptic paraboloid. The equation of an elliptic paraboloid is z over c equals x squared over a squared plus y squared over b squared. AB represents the scale factor along the x and y axis, affecting the width of the paraboloid along the x and y direction. C represents the height or depth of the paraboloid along the z-axis. This surface is called an elliptic paraboloid because the vertical cross-sections are all parabolas, while the horizontal cross-sections are all ellipses. The simplest form it takes is z equals x squared plus y squared when a is equal to b, which is equal to 1, and we can refer to as paraboloid only. This is the graph of the elliptic paraboloid when visualized in 3D. The equation z equals x squared plus y squared represents a mathematical surface known as a paraboloid. It's a 3D shape formed by rotating a parabola about its axis of symmetry. The plot illustrates the shape of the paraboloid in 3D space. It resembles a bowl or a cup with the opening facing upwards. The curvature of the surface increases as you move away from the origin along the x or y axis. The paraboloid exhibits symmetry about the z-axis, which is evident from the shape of the plot. This symmetry arises from the fact that the equation only involves the squares of the x and y, resulting in rotational symmetry around the z-axis. The focus of the paraboloid is located at the origin 0, 0, 0. This is the lowest point of the paraboloid, where z has its minimum value. The axis of symmetry corresponds to the z-axis and runs through the center of the paraboloid. Paraboloids are commonly encountered in various fields, including physics, engineering, and optics due to their unique properties. For example, paraboloid-shaped mirrors are used in telescopes, satellite dishes, and headlights to focus incoming light or radio waves at single point. Paraboloid reflectors are used to focus sound waves, such as in satellite dishes for receiving signals. Paraboloids are also used in design of antennas, satellite dishes, and solar collectors due to their ability to focus energy. Now, let's move on to another polynomial function when graphed in 3D space. This is a hyperbolic paraboloid. The simplest form is represented by the equation z equals x squared minus y squared. This does not possess an axis of symmetry or focus in the same way as an elliptic paraboloid, because it does not exhibit rotational symmetry about any of the axes. The saddle shape of the hyperbolic paraboloid makes it asymmetrical along both the x and y axes. Similarly, the hyperbolic paraboloid does not have a focus, unlike an elliptic paraboloid. The saddle shape causes the surface to curve away from the origin along both x and y directions, resulting in a more complex structure without a single focal point. Despite these differences, hyperbolic paraboloids are still valuable mathematical surfaces with unique properties and applications. They are commonly encountered in fields such as architecture, engineering, and mathematics, where their distinctive shapes and properties are utilized for various purposes. This is the third and final shape, which is a double cone. In geometry, double cones are also referred to a bicone or dicone, and the name is derived from Latin bi and Greek di, both meaning two. It is a three-dimensional surface of revolution for a rhombus around one of its axes of symmetry. Equivalently, a bicone is a surface created by joining two congruent right circular cones at their bases. The equation of a double cone is z squared equals ax squared plus by squared, where a and b are constant. So the quadratic equation for its simplest form will be z squared equals x squared plus y squared. The double cone consists of two symmetrical opposite-facing cones joined at their vertices. It resembles an hourglass shape. The vertical cross-sections of a double cone are hyperbolas, while the horizontal cross-section are ellipses. The double cone exhibits symmetry along its axis of rotation passing through its vertex. Double cone serves as a fundamental geometric shape in its mathematics, forming the basis of understanding all of the conic sections such as ellipses, hyperbolas, and parabolas. In physics, the double cone serves as a visual representation of the concept of equipotential surfaces and field diagrams, facilitating the understanding of electric and gravitational fields in physics. With this, we come to an end of this demonstration program. I hope this has shed light on the importance of spatial visualization and sparked your curiosity to explore further. Thank you for watching.